Topic today is model fitting. Yes, model fitting. That's a topic that is extremely widespread and used in machine learning, in data science, in modeling for performance evaluation, in statistics. So it's very important to understand it well, but as we will see, it's fairly easy. So model fitting, what does the drawing, the cartoon here illustrate? Yes, but when we model, in fact, we have a very simplified model of things. So we should not expect to have a detailed modeling of everything, but a simplified model that allows us to do something. Like here we recognize it's a castle. Here is an example that I found in the literature. This is data that is gathered about the spread of an infection of computers this was worldwide. So I plot as a function of time, every hour is the number of infected hosts, and we see of course that it grows very fast here. Now because it grows very fast, and by the nature of infection, an exponential model of this kind here, that is saying at time t, the number of infected hosts varies exponentially with t. It's in the nature of infection because for an infection to spread, you need hosts to contact other hosts, and the more there are, the more they are infected, so it will grow exponentially. Of course, not forever, because we have a finite population, but here we're just at the beginning of an infection, so if it's a public, something that spreads publicly, there is potential for much more. So assume we have that, and we ask the question, what I have is really the blue dots. Every hour I have a number, and I would like to see how do I fit the red curve? How do I fit a formula like this? So how do I find A and alpha? Alpha is the parameter of interest because it will give me, for example, the doubling time. How much time does it take to double the number of hosts? So that's really the critical parameter that tells me about the speed of the infection. Here I did what is called a least square fit. I'm sure all of you did that already. So how does that work? You can ask MATLAB or Python numerical programs to do it for you. But what happens when we do this? Any clue? We minimize the square error, exactly, between the blue dots, which are the data, and the red line that I'm doing that here. So this is what I did here, and this is what I obtained. But of course, after a few weeks of the performance evaluation course, there's a question that should come immediately. That of the scale of the data. Here I plotted the data in natural scale. If something is growing exponentially, we are more likely to plot it in log scale. Here, before going to the log scale, here is the result of this plot. If I ask my plotting software to plot the curve, it will plot it, but it will also compute the parameters, which are the A and the alpha. And I find here alpha in per hour. So that means that the mean doubling time is this. And if I extrapolate, I say, starting here, if I continue the red curve, I know now the parameters of the red curve, so I can say if I continue it to plus 6 hours from now, here is the number I will have. 100,000 hosts will be infected in 6 hours from now. This is what the least square fit will do. But of course, if things are growing that fast, we are more likely to plot them in semi-log scale, natural scale on the x-axis and log scale on the y-axis. And here, by the way, that's a much better way to verify whether the growth is truly exponential. On semi-log, an exponential growth will be translated by a straight line. So the blue dots do appear to be a line. And I can plot a straight line by asking my preferred plotting software to put the line, which is now a straight line, between the blue dots. Right? If I do that, it turns out that I will find slightly different values. My alpha will be different. The mean doubling time will be larger, and the prediction at 6 hours will be much less. So I go from a prediction of 100,000 infected hosts to 39,000 infected hosts. Right. They are different. We will see how to, in this case, how to do things to differentiate between those two different things. But the first take-home message is this is quite natural. This is what you will see. So when people do predictions or analysis of data and say, we have estimated that the doubling time would be that in 6 hours we would have so many, probably each of them using different methods will find different values. So should be a bit careful about that. Here I looked at the two plots in natural scale and in log scale. So I did the plot which was a straight line, then I converted to the natural scale. Here's what I obtained here. Do you see a difference between the fit? Well, first we see that the two curves are different. So which one should I believe? I mean, I've done just the natural thing that everybody does. I have a cloud of points. I want to find the best, very simple model. I ask MATLAB or Excel to do a least square, but depending on whether I do the log scale or the natural scale, I find different things. That's embarrassing. So to get out of the embarrassment, let's try to analyze what has happened here. Do you see a difference in the fit here between the green and the red curve? Well, I know the answer, so I see the difference, but well, the red curve is very balanced. The error is about the same size everywhere, right? Whereas the green curve here has a large error there and much smaller errors there. Right? So the green error is trying less hard to be exact in the high values than in the small values, whereas the red curve is trying to be as exact everywhere. Right? So that leads us to what happens when we do a model fitting. We will do errors. The model is not perfect. If there would be a true perfect model without error, then it's a much easier problem. Here, there is never a model that will be perfectly fitting. So we need to understand what is the nature of the error. And the first, yes, before doing that, which one would you prefer if you have to do this? Which one would you do? Voilà. The vast majority says B, the log scale. A few people are still adept of the natural scale. Well, let's wait, let's postpone the answer a bit here. By simply looking at that, yes, we could say log scale because it grows exponentially fast. This is probably what would have been done naturally without asking the question. But if we ask the question, we need perhaps to understand more about what is model fitting, and then we'll come back to the answer to that. So model fitting is doing exactly this here. It means I have a parametric model of a data. Here it's simple data, it's just a single number. It can be applied to more dimensions, but let's stay with just one dimension. So the key thing is, most often there is non-parametric model fitting with kernels and splines, but we won't go through that. Here I assume I have a model of the data that depends on a parameter, theta. And this parameter is the thing to be found here. Perhaps I will have different models. I may want to discriminate between several. We'll talk about that when we do tests. But here for the time being, assume I have a single category of model, and the problem is to find the parameter. For example, here, my model is this one. I think the data grows exponentially, and my only problem is to find A and alpha. Right. That's the simplest example, but quite general example of the model fitting problem. And when we fit the model, we want to write that the thing that we have measured is equal to the true value of the model plus noise. That's very much what we did when we talked about confidence interval. It's the same thinking. So we think that what we have obtained is the result of a clean, simple model somewhere that has been corrupted by noise, or that has been generated by a simulator that has produced the noise to us here. And the problem is to find the unknown parameter while being aware that there is some noise here. There are multiple ways to write equivalently the same model. In our case, here this is the model we have. If I take the log of this, I obtain exactly this, which explains why in log scale it is linear. Log of y is a constant plus alpha ti. Those are strictly equivalent things. So at this level, I don't see why one would be better than the other. Here the parameter is the sequence, those two numbers, A and alpha here. There are two schools of thought about model fitting, three I would say. There is the signal processing, the statistics, and perhaps the pure ad hoc, where we don't try to understand what we do. So I will ignore the third one. The first one, the signal processing interpretation, assumes there is a well-defined thing called a score. So the score is something that allows to tell us whether the noise is reasonable or not. More precisely, when we do model fitting, we transform the model fitting into an optimization problem, where the goal of optimization is to minimize the noise in some sense. And since the noise is, there are many values, we aggregate all of the noise values into one score, which we interpret as a penalty function. So we want to find the theta that minimizes the penalty of the fitting, right? Because the fit can never be perfect here. So far, it's simple. The only annoying thing is that there are multiple scores. And really the gist of model fitting is to be sure that the score we have makes sense for the problem at hand. What we did was to take a score that was this one. When we do least square minimization, the score is the sum of the noise square. Right? If it's multidimensional, it will be the Euclidean norm. Very often, we want to give different weight to different observations, so we have somehow some weights that may be obtained an additional parameter or maybe a priori fixed. This is called weighted least square. Those are the most widespread methods. The huge majority of papers in classification exercises and model fitting use those scores. Right? But in fields of signal processing like compressive sensing, some people have observed that it's sometimes even better to use scores that don't square. After all, that's the more natural thing. I mean, why do we square to measure a distance? If I take the total penalty of a trip measured as a distance, I'll take the sum of the distances, not the sum of the squares. We will see there are good reasons for taking squares. It is because it makes the computation very easy. But if we don't have computers. If we have computers, this is practically as easy as that, so it is more and more used as well. It's called the L1. This is the L2 norm of the noise vector. This is the L1 norm of the noise, so it is often called the L1 score, which is the sum of the absolute value of the noise here. If it's a multidimensional noise, we take the sum of the absolute values of all the coordinates. So, and we can weight that here. So I have at least multiple scores. Which one should we use, right? In signal processing, this is typically done by ad hoc evaluation inside a given field. For example, if we want to do very effective, very economical analysis of huge images, if I have a very large database of very large images, one way to do model fitting on these images. Model fitting is, for example, deciding whether whose face is on which image, right? Then very often we use these scores here because this gives a very robust and a very, very robust methods. We'll talk about that later. There is another interpretation which comes from the statistics department of things, which is more appealing, but in practice is sometimes more complicated to use. It consists in assuming that we can say something about the noise as a stochastic object. For example, classical things that would be used is to say, I assume that the noise is a sequence of values that are independent and come from a noise distribution. Noise distributions are typically whatever distribution, but they are typically centered around zero. And invariably, very often, people use Gaussian. So this is called sometimes white Gaussian noise. White because it's non-correlated, and Gaussian because it's Gaussian here. So, but I could say the noise is added to the value here, or the noise here is only relative, right? The difference between 1 and 2 is saying what I observe is a true value plus some additional error that has been done. But the error is on the value itself or on the relative value rescaled with respect to the size. Very often number 2 makes more sense, right? If I measure something that's very large, if I measure a distance from Lausanne to San Francisco, the accuracy I have is, if I have an accuracy of a few centimeters, is extremely high accuracy, right? If I measure the length of these devices and have an accuracy of centimeters, it's not very accurate, right? So I should not expect to have the same accuracy on huge numbers and very small ones. So this is something that often makes very much sense. Model 3 is if we believe, or if we receive the data in log scale, so then it's the same as 1, but in log scale here. For each of those models, we have a nuisance parameter that's added. We need to estimate A alpha, but also sigma. Not that we really are interested in sigma, perhaps, although sometimes we are. We will see for prediction or confidence interval, sigma will tell us something about the data that we have. But if we do estimation, as we will see, we translate this in an optimization problem where the parameter sigma will show up. So when we have the statistical interpretation, we have to model the noise, which may mean adding parameters to the noise here. So how do we do the statistical estimation? The signal processing estimation is very simple. It's an optimization problem. It's simple if I have an optimizer. That will not be the topic. How do we go from the statistical model to something concrete? Well, there is a classical method which is called maximum likelihood, which is the method of choice in statistics, which we have perhaps already discussed. I'm sure you have seen also already. The principle is how to solve a problem of the nature we had before. What is the nature of the problem? The problem is I have been given some data, which is my y, my measurement here, which I assume comes from some model. So we can think of it as it comes from a simulator. You know by now, since you've gone through lab 2, you know how to simulate practically anything. So if I give you this model, if I give you A and alpha and sigma, you can generate 1 million samples of y. Right, so you can do that. And in this maximum likelihood estimation, we think that the data we have is given by a homework. Somebody has done the homework, but we don't know what is A, alpha, and sigma. And our goal is to find A, alpha, and sigma. The most classical method is to use maximum likelihood, which consists in saying, I will compute for the unknown parameter theta, here theta is A, alpha, and sigma, the value that maximizes the likelihood of the data. The likelihood is the PDF here, right? So if I consider y as a vector of all the data, if this model looks very complicated, but it just means the different numbers y1, y2, y3 are Gaussian random variables that are independent with a mean which is this, because this is a Gaussian random variable with mean 0. If I add this, this is a constant. No, it's not constant for me because I don't know A and alpha, but for who did the simulator, it was a constant. A and alpha are known. So the likelihood is to be understood for somebody who is doing the simulator, knows A and alpha and sigma. So this is a constant plus a random variable which is Gaussian. This becomes a Gaussian random variable with mean mu for I equal to that here. So that gives to this formula for the density, the PDF, which you can have by looking up the formula for a Gaussian random variable. Y1, Y2 are independent, so the PDF is the product of what we obtained for every Y. And if we number crunch everything, we obtain that here. So the problem becomes find A, alpha, and sigma that minimize this when we treat Y as given. I have obtained the data. I want to infer A, alpha, and sigma. Maximum likelihood says find the value of the unknown parameter that maximizes the likelihood of the data that you have. So we do things in reverse order. The likelihood, usually we think of it, it's a function of an unknown data, the random output. with a known thing, which are the parameters. Here we inverse the logic. What we have seen is now treated the random data as fixed, and we don't touch it, and we want to maximize here. Why do we do this? Where intuitively we say we don't know what the parameters are, but we are more likely to see things that are more likely to happen. So if we don't know what value give to the parameters, the ones that make this data more likely are the ones that make sense here. It's a weak justification. There is a stronger justification that says that this is a robust and consistent estimation method. Robust means that robust and consistent means that if the sample size gets large, of course, if you observe 2 data points and you have to estimate 2 parameters, it's probably not much that you can say. But if you estimate 1 million data points, probably you'll have a good estimate. So as the number of data points increases, the result of this optimization converges to the true values under not always, you need some hypothesis, but under a very large class of hypotheses. So it's not necessarily the best estimate if you have small sample, but if you have a sample that is not too small, it is one that at least is safe here. Let's do it in general for the most general model fitting of the kind we've seen. So here I have some data point y, and I have some generic function f. For every I, I have an f of I, and they depend on some parameter beta. For example, in the case before, beta was a and alpha. Then we have this first equivalence theorem that says the maximum likelihood estimation, if we assume that the data is equal to the explanatory model plus additive IID Gaussian noise, with this IID means in particular the variance of all the epsilons is the same, then this is the same as least square. So the solution of the maximum likelihood estimation consists in minimizing this. So what is this? Fi of beta is the error I do. Y is my data point. Fi of beta is the ideal value it would have if the true parameter is beta, and this is the error. So if I if I minimize the sum of the square, I am doing least square estimation. Well, it tells me the maximum likelihood estimator of beta is exactly the value of beta that minimizes the least square. So it establishes equivalence between the signal processing interpretation, where the score is the least square, and the statistical explanation, the statistical interpretation, which assumes that the error terms are Gaussian IID. So that's a very strong and powerful theorem, even though it's not very complicated, because it explains to us what we do when we do least square. When we do least square, we would do the standard estimation if the error is IID Gaussian, which will also help us to understand whether this is appropriate, because we can estimate the errors by looking at the error and see whether they are reasonably IID Gaussian or not. That will lead us to at least have some hope to see whether this type of fitting is appropriate or not. It tells us a bit more. It tells us also, it gives us an estimate of the variance of this noise model, which is 1 over I, the squared of the errors, which is a formula we used when we estimated sigma out of independent things. When we estimate the mean, for example, we had a formula like this here. Where does it come from? I usually don't do the proofs in this course. The proofs are all in the lecture notes. But let's do it here for this time, because it's very simple and it will tell us that there is no magic here. This is the likelihood that I had written before. So I am given the data points y1, yy, and if the true model is this one, then this is the PDF of seeing exactly the value y1. And now we say, I want to maximize the likelihood. Since this likelihood has this form, it's more convenient to take the log, so which is called the log likelihood. For many models, this is the case. So if I take the log of this, I obtain the log of this big part, which gives minus I log sigma, also minus I log 2 pi, but I is fixed here. It's my number of data points. In my optimization problem, I is fixed. And 2 pi is also a constant. So when I look for beta and sigma that minimize or maximize something, I can ignore those terms. I put those terms here. It means minus a constant. And this is the log of this term here. So we have to maximize this. There's plenty of minus signs, so it's the same as minimizing this. So we need to minimize this quantity. And now that becomes completely tractable. I do it, I have a problem in two variables, in a vector beta and a variable sigma. If I fix beta, I can look for the sigma that gives the minimum for a fixed beta. Right. So if beta is fixed, I have a function of sigma only. I can take the derivative, and the derivative will give that. I over sigma minus 1 over sigma cubed times this. I set it to 0. We need to do a few other checks to see by 0 we obtain effectively a minimum and not a maximum. That's easy to do. Well, that's a high school exercise, right? This function, find the minimum of this function. If instead of I and this y, I would have log sigma plus some constant over 2 sigma square, right? And we find this formula. The max, the mean of this, is obtained when sigma is equal to this value, 1 over I, the L2 norm of the error. So that gives us the part B of the result we had before. And now if we continue, if I say, so if I want to optimize, I still need to optimize over beta, but certainly once I have whatever I do over beta, the sigma should be that one, because for any fixed beta, there is no other sigma that has a beta score. So I should use sigma equal to that. If I plug sigma in this formula here, you will see that this and that cancel out, because sigma square is exactly equal to that times 1 over I. So this complete term here becomes a constant when I replace sigma by this value. So I know for every beta what is the best sigma. I still need to find what is the best beta, which I don't do, but I just say the following thing. The best beta is the one that minimizes minus I log of sigma hat of beta. In other words, that maximizes this, because that's the likelihood. Otherwise, that's the one that minimizes this quantity. I is fixed, log of sigma or log of sigma square are minimum at the same time. So what we want is to minimize sigma square of beta, which is exactly the L2 norm of the error, which is what the result was saying before. So we have given a proof of this result here, which essentially says minimizing L2 norm is exactly the same as assuming additive white noise of constant variance has been added to the data. Right. So in the specific case that we have here, then we have to ask MATLAB or NumPy to minimize this quantity over A and alpha, which is a highly nonlinear exercise, but since it's in dimension 2, in MATLAB fmin search will find easily a solution. And we know that at the solution we should have this relationship here. This is what I did for the model, but then I can do the second thing I mentioned before, look at the residuals. The residuals are the errors, right? What do? I replace A and alpha by their optimal value, A hat and alpha hat, and I do the difference, Y hat minus A alpha hat. I obtain some estimate, a noisy estimate, but probably not a too bad estimate of the epsilon I. Of course, I don't know the true epsilon I because I don't know the true A and alpha. But if my estimate of A and alpha are not too bad, I have a fairly good estimate of the epsilon. This is what I plotted here. Right. And then I should convince myself to accept this least square fit, that this is white Gaussian noise. Right? This is an IID sequence drawn from the same standard normal distribution. Does it seem okay for you? No, it's really stretched to imagine that this is IID Gaussian. Right? We will see formal methods to verify that something is Gaussian, but here we see clearly that on the left they're all very small, very close to 0, and on the right they become very large. So there is something that is happening. Here I look at the fit in log scale. in log scale, so I do the same thing. I do the fit. Of course, I obtain another fit. I have another optimization problem to solve, which is now linear. If I call x, or if I give a name m to this, or L to this value, I have to fit log I, which is data, L plus alpha ti. So it's a completely linear thing. So it will be easy to solve the optimization problem. We will see it has a closed form, in fact. And I did the same thing. I plotted the estimation of the residuals. Do they appear to be Gaussian? Hard to tell. But certainly, if I have to choose between this or that, I will prefer the one on the right, which means that the fit that was done in log scale is more reasonable than the fit that was done in natural scale. Voilà, that's our first take-home message. If we are in trouble, if we do a fit, we should think. Here, the exercise was easy because I forced you to look at two fits and ask which one is good. But the problem is most of the time, we do one fit. We do least square, and that's the end of the story. And we're happy with that because we've programmed it, and it took us 2 days of programming to do it, and we have an estimation. And it's probably not too bad because the red and the green curves are both following the data. But there was a much better fit that could be done by someone else. So you might as well think, am I doing the right thing? What is the model that I am implicitly assuming when I'm doing that here? So what we have seen is that given a model to be fitted, we have the equivalence between least square score and saying the noise is ideal with the same variance. The key thing here is the same variance. And this is what was, this is what was not true in this model here. We see that the noise here is very small and here is very large. That means that all data points don't have the same variance. It's one of the points that is always missing when we do least square fitting. When we do least square fitting, we assume implicitly the error terms are of the same order, are similar in magnitude at all the data points. This is why the blue fit was trying to have the same error everywhere, so it was putting a line that is the same everywhere. When it was doing it in log scale, it was in log scale having the same error everywhere, but not in natural scale here. So one way to rescue this type of fitting is to put weights here. Right? So for example, here we could put a weight that is proportional to the value. If we think the noise increases exponentially, then we could have a weight here. If we give a weight W to the noise, this is equivalent to assuming that the variance of the noise is reduced by W squared, or the standard deviation is reduced by W. If we give more weight to a noise, that means we want the fitting program will, the penalty of this noise is very large, so we'll try hard to have it smaller, because a small increase in this noise level gives a large penalty. So you'll try to fit less well the other points rather than this one, which statistically corresponds to assuming that the variance of the noise for this point is small. So the fit should be rather exact at this point. So this is why we have this here. And to prove that, it's the same proof as what we did a minute ago. So we saw 3 possible models for the virus expansion data. Which score corresponds to which model? So I have 3 scores, 3 signal processing interpretation, 3 statistical interpretation, which corresponds to what? So the unanimity is for A, which is correct. Right? That's the... In fact, if we compare, so we see that model 1 is probably not very good for this fitting. Model 3 is better. If we compare model 2 and 3, in fact, they're approximately the same. If the noise term is not too large, then this is, by taking the log of model 2, this is saying log y is equal to this plus log of 1 plus epsilon. Now, strictly speaking, if epsilon is Gaussian, log 1 plus epsilon is not Gaussian. It's a complicated, no, it's a non-standard distribution. But if epsilon is small, log 1 plus epsilon is close to epsilon. So it will be close to that model, which is model 3 here. So the take-home message is it's practically equivalent to assume that the error is of constant magnitude in relative terms, or to take the log of the model here. So take-home message at this stage. In order to fit a model, you need to find an appropriate score function and reason about it. Right? You cannot simply say, I do least square because I've seen in MATLAB that it works and gives a fit. There are multiple ways to find a fit. You need to take decisions. You have 1 zillion points, you have 1 zillion errors. Why do you give more value to that error or to that one? You need to reason about it. Right? One way is to consider an explicit model. That's a statistical approach, which has the benefit that we can validate it a posteriori by looking at the residuals. Now, in theory it's good, in practice it is good only if you find a fixed point in your validation. You pose a model, you look at the residuals, they look okay, but if they don't look okay, you change the model, but the risk is after some time you don't find a model, which often happens, not always of course, but often happens there. A common mistake is to ignore this discussion about the score, and in particular to assume that the noise have the same variance, which is what we do when we do least square fitting. And that's it for now. What we will see also is that once we do model fitting, if we have some estimate of the noise, and if the model fits very well, then we can do a bit more, because if we think the model is not too unrealistic, like model 3 for our data here, we could perhaps believe in the model, and if we believe in the model, we can have confidence intervals for the estimations. What is the error bars we can put on alpha, for example. I give you this value of alpha, but how sure am I about this value? Someone else gave me a completely different value, so how sure am I about this? This is what the statistical approach, when it works, will allow us to do. Right. Yeah, let's continue. So what we will do now is go a bit deeper into the least square, because the least square, even though I criticize it a bit, but we've seen that we need to do it with care, but when we do it carefully, it is extremely powerful because the computations are very simple here. So we have seen this first result, but we have a bit more. We have that if we want confidence, so this is how we compute the estimation for a generic model where we believe the noise is having this property of being IID Gaussian with fixed variance here. Then we have something that can be used for computing confidence interval. It tells us that if I compute this matrix of second derivatives, what is f? F is the function that maps the parameter beta to the data point y. So beta is unknown and typically a continuous parameter, so I can compute the derivatives. If I take the second derivatives with respect to all, if there is only a single parameter, then the second derivative of fi with respect to this parameter, but usually the parameter has several values, like we had a and alpha before. If I take the matrix of second derivative divided by sigma square, if this happens to be invertible, then approximately the estimate given by the minimization problem we saw in the previous slide, minus the true value, is approximately Gaussian with zero mean, and covariance matrix the inverse of that. Here. So in other words, we have found what I called previously a pivot, which is the crux to find confidence intervals. We reason about unknown things, but by magic, when we divide by sigma hat and multiply by 1 over square root of n, all of a sudden the distribution of that is known, even though the parameter is unknown. This is exactly what happens here. Whatever the values of the parameter beta, we assume sigma is known, but sigma we can estimate it. Whatever the value of the parameter beta, the error, the estimation error we're making, that's the estimation error on the parameter beta, is approximately Gaussian with a covariance matrix here that is fixed, that depends only on the model, on the generic form of the model, not on the specific value of the parameter beta here. And there is an alternative asymptotic form that I will discuss a bit later to use that. But let's apply this to the example at hand. This is the model we had. Log y is log a plus alpha ti plus noise here. So the function fi, I drop the fi of a and t and alpha. So I call, to avoid dragging log all along, I call a prime log a. So the function fi of a prime and alpha is given by this, right? So if I call beta 1, the first parameter is alpha and a prime is the second. The derivative of this with respect to the first parameter is ti here, and the derivative with beta 2 is 1. So I can compute the matrix obtained by all the cross derivative, the formula that's given here, right? The sum of all those cross derivatives. Whoops. Here we are. It's a 2 by 2 matrix because I have two parameters, beta 1, beta 2, alpha and a prime, and the values are obtained here. K11 is 1 sigma squared ti squared, etc. I have those values here. So my matrix K is equal to that here, right? Which means that if I take the... why am I repeating the same thing here? I think this is just twice the same, yes. So this is the matrix K given by this prediction here. Now what is this sigma in a more compact form? Ti square is the mean of the times t plus st square, which is the sample variance of the times. It has nothing to do with the data I'm observing, but the times ti at which I observe the values here, I can compute also their standard deviation. So this is the matrix K. In things like MATLAB or other numerical software, the inverse of K is called the variance-covariance matrix, because this theorem tells us that approximately the error is Gaussian with a covariance matrix given by the inverse of that. So what is the inverse of that? Well, it's a 2 by 2 matrix, so I can look up Wikipedia how to invert a 2 by 2 matrix, and there's a closed form formula. It's given by this here, right? So it means, what does it mean? It means that I know the distribution of the vector of errors, A and alpha. Let's, for example, apply that to just the first dimension, which is alpha. The covariance matrix is here. That means that the alpha, the error on alpha, has a variance, which is sigma square divided by IST square, right? So the true alpha minus the estimated one is Gaussian with this variance, which will allow me to compute a confidence interval with probability 95%. It will be plus and minus 196 times the square root of this. So that will give me a confidence interval for A, for alpha. For A or for A prime, I think the prime has disappeared in this thing, we have the same thing here by looking at this term, which gives me that. I could even have more. I could have, if I am using something that involves both A and alpha, like I will be doing if I do, for example, a forecast in the future. I will have a linear combination of A and alpha. I can have the error on this linear combination by using the covariance matrix here. What would be a confidence interval for alpha? The majority says C, which is wrong. I mean, of course, it's hard to see because we don't have two slides at the same time. But for alpha, we look at this. We take the square root of this, and that gives answer B here, right? Which I did numerically in this example. So we believe the log scale plot is more realistic. So I did I computed the confidence for that, and I found that here is the value. So we see they're still fairly large here, right? So if I want to do a prediction, I will also have the same uncertainty about the prediction here. So this is what linear regression can tell us in the good cases when the statistical model fits well. We will now do a break, 15 minutes or 13 minutes, and after the break we will see in general the power of linear regression and why it is so often used.